Welcome everybody today. Today is the turn of Lafuerza to do our seminar.
Good afternoon. I'm going to tell you about this work I've been doing the last year here at the IFISC in collaboration with Bere and Raul here. And the title is Synchronization Properties Phenomena in Complejos Systems. The outline of the talk is the following. First, some introduction and background, some previous results, some new results, then discussion and conclusions. So this work deals with synchronization. So what do we understand by synchronization? Well, we speak about synchronization in the context of dynamical systems, that is a system that changes in time. Basically, we say that two or more systems are synchronized when the change of their state over time is somehow correlated. There are different technical notions of synchronization. The simplest is phase synchronization, and we say that two systems are synchronized in phase when they have the same state at the same time. There are other more general notions of synchronization, such as synchronization frequency or synchronization with some time lag, or other ones, but here we focus on this most simple case that is phase synchrony. And why do we study this synchronization as physicists? Well, synchronization is a widespread phenomenon in nature. It happens in many very different systems, ranging from peacemaker cells in the heart or neurons in the brain, population of fireflies, chemical reaction, arrays of Josephson junctions, which are some kind of electronic circuits, and many others. So here we also focus on the synchronization of many units among themselves, not the integration of just 2 or 3 units, and not the integration of something to external with external cycle, but the synchronization of a system of self-interacting units. And all those systems have in common that they are composed by many units, and usually each unit has some rhythm. The units are themselves oscillatory. They have some intrinsic rhythm. But those units are not identical to each other. The rhythm is not exactly the same from one another. Because in nature there are not two cells which are exactly equal, or two electronic circuits which are exactly equal, or two other which are exactly equal. So we have a system of many units. Each of them has slightly different rhythm, but under some conditions they manage to acquire a common rhythm, a common frequency, and they synchronize. So we're looking how this happens. And to study this problem, we build a mathematical model that is simple enough so that we can analyze it and hopefully understand it, but still is rich enough to show the phenomenology we're interested in and to correspond qualitatively at least to these more complicated phenomena, and possible also quantitatively so that we can make some quantitative predictions. And yeah, then the minimal ingredients of such a model are just those ones, an ensemble of non-identical dynamical units plus some coupling. Because without coupling, without interaction, there is no way the system can synchronize. So, in this spirit, Kuramoto in 1975 proposed this model. In his model, each unit is a phase oscillator, so the state of each unit is described as a phase. That's a number between minus pi and pi. And when uncoupled, the dynamics is given by this part of the equation, so the phase increases in time with a constant frequency. So this corresponds to a rotator, a frequency which is increasing linearly in time. Now the units are not identical, and this diversity is introduced in the model by taking the natural frequencies of each unit from some probability distribution, with some average and some variance. And then the variance would be a measure of the diversity. The higher the variance, the more different are the units. Then the units, we have a system of non-analytical units. Each of them rotates with some natural frequency, but then they are coupled through this term. In the coupling case, the coupling strength ends the total number of units, and the coupling function here is the sign function. In principle, this function can be any function, but it has to be 2 pi periodic, since this is interpreted as a phase. And then to be attractive, the simplest one is the sign. We can see that this is an attractive interaction, since if the phase of j is greater than the phase of I, then this term is positive, so phi tends to increase towards pj, and if phi is smaller, or if phi is greater than pj, then this is negative, and then phi tends to decrease against towards pj. So here we have this system of units coupled, and to measure the degree of synchronization, Kuramoto introduced this order parameter, which is basically the complex sum of the phases, and this corresponds basically to the center of mass of the system. So the units are placed in a circle, then this is gonna be the center of mass. And when all the units are very close to each other, then rho, the modulus of this complex number, is close to 1. And when the units are scattered uniformly through the circle, then rho is close to 0. So in this way, rho is a measure of synchronization. If rho is close to 1, the system is synchronized. If rho is close to 0, the system is not synchronized. And again, by now, with the other parameter, we can rewrite the coupling term, where now the coupling only appears through the global parameters rho and psi. And this is possible because the coupling is all-to-all, is mean field. Of course, and yeah, what the system gives is what the principal one would expect. For small values of the diversity, small values of the variance of the distribution of natural frequencies, the system is synchronized, so the synchronization degree is large, is close to 1, and then by increasing the diversity, this synchronization decreases until very low values. In the thermodynamic limit, in the limit of many oscillators, this happens through a second order phase transition. So there is a critical value of the diversity over which the synchronization degree is exactly 0. But for any finite system, as this one, which has 500 units, the synchronization becomes very slow, but not exactly 0. This result is very general. It holds basically for any distribution, at least for symmetrical unimodal distribution, which are the most common, and also holds for a system with stable noise, white noise. Then this is the most simple model related to synchronization, or one of the most simples. And of course, a lot of different variations have been studied, such as different coupling functions. Also, in this model, each unit is coupled to all of them. The unit I is coupled to all the rest of units with the same intensity. So this has been studied also what happens when the coupling depends on the pairs of the elements. So that corresponds to putting here some k depending on the pair. In this work, we consider a modification of this model, first proposed by Kuramoto again and Kuramoto in 1996. And in this case, the dynamics of the individual units is given by this part of the equation. Now the units are not rotators, they are called active rotators. And the dynamics is, when omega is smaller than 1 in module, this system has two fixed points. So one stable and one unstable, so the system always goes to the stable fixed point. And if we perturb it slightly, it goes back to the stable fixed point. But if we perturb it over some threshold, which in this case is this distance, instead of going back, the unit experiences a excursion over the phase space. And this is interpreted as a firing or spike. So that's why we say that this is an excitable system. So when omega is smaller than 1 but close to 1, we have the unit is excitable. Now again, we will consider a system of non-identical units, and we will do so by taking this parameter from the probability distribution with some variance and some average. And we will consider that the average is smaller than 1 but close to 1, so that on average the units are excitable. And we have a system of excitable units coupled, globally coupled, this term. Now, due to the diversity, some units will have omega greater than 1, and if omega is greater than 1 here, this term is always positive, so the unit becomes oscillatory, right? So in our system, we will have some units which will be excitable, and some others will be oscillatory, and some others will be basically stable. When omega is small, this is basically a stable unit. So we have a system of different units, some of them excitable, and most of them excitable, coupled globally. And we want to study what happens as the diversity is increased. And what happens is basically that there are 3 different dynamical regimes. First, for small diversity, for variance of the distribution of control frequency small, we get a stationary state, static state, in which this is the phase of different units as a function of time. And here all the units go to a fixed point, so they are static, they are stable, they do not change over time, and they are very close to each other, so the system is very synchronized, but it's static. Then by increasing the diversity, we enter a regime of collective oscillations, collective coherent oscillations. Here the units, the phase of the units change over time, they are doing some oscillations, and they do them synchronously. They have the same frequency and they rotate at the same time.
Which are the different colors?
There are different units. This is the phases of different units taken at random. So yeah, the ones with higher omega will be higher than the others. But the thing is that almost all of them do experience these oscillations and in a coherent way at the same time.
Which is the average value of omega?
Here, this corresponds to 0.95, I think. So that the picture is something like this on average.
But not in all 3 cases?
No, not yes, in all 3 cases.
In all 3 cases?
Yes, what changes is the variance. So that in this system, they are basically all the same, very similar. They are all basically this one. Whereas in this case, there are more which are more stable, and some of them which are oscillatory. And it's those which are oscillatory in nature, in a couple, they are able to graph somehow the others and make the system oscillate as whole. A further increase of the diversity leads to a regime where some units are static, they are basically fixed over time, others fire at different speeds, some very fast, others not so fast. So here there is activity, but there is incoherent activity. The system as a whole is basically static over time, but some units fire, some others don't. Again, to describe the collective state of the system, we use the Kuramoto order parameter, and now also this other parameter, zeta, which is defined in this way. And this parameter is 0 when the system is stationary, and the system is stationary as a state in which the global parameters, rho and psi, are constant in time. Psi is the global phase, and rho is the diffusion degree. So when these global parameters are fixed in time, zeta is 0, whereas when these global states corresponding to the center of the system vary in time, then zeta is different from 0. So this zeta assigns us the state of collective phi, non-stationary state. Well, our system is here. To get a closer idea of what we are talking about, I can show you a little program that shows a system like this. Here we choose a natural frequency of 0.87. Here the variance for small variance, and this is for a Gaussian distribution of frequencies. You see that the system here's all the units represented in the circle. They all go to a fixed point basically, and they stay there. So this is the static state I showed you before. And here the synchronization degree is usually very large, so close to 1. Then for an intermediate value of the diversity, we see a different, well, not in this case. This, of course, is a finite system of 10,000 or 1,000 units. So what happens depends on the realization of the diversity. But here we see that in this regime, the system as a whole experiences some oscillations. So the green dot represents the center mass of the system, and the green line represents the degree of synchrony. So here we see that this global phase, this global parameter, the center of mass of the system, does rotate. So the system as a whole rotates. Then there are some units which have very large value of the natural frequency, and they rotate higher, at higher speed, but the important thing is that the system as a whole in this regime experiences some oscillations. Then for values of the diversity larger, we arrive at a disorder state. Here there are a lot of units which are oscillatory, some others will be around here static, although we cannot see them. But the important thing is that the center of mass of the system, so to speak, is basically constant on time. It's drifting around, which is a finite system, but it's basically constant. There is no collective activity, and you see that the significant degree is smaller in this case. And this can be seen in this graph. So for small values of the diversity, we are in this fish regime where the synchronization degree is large, but there is no collective activity, so zeta is 0. Then we enter a state of collective motion in which the synchronization degree is still large, but there is collective activity, assigned a non-zero value of zeta. And then we again enter a system with no collective activity, in which the synchronization degree decreases steadily. This was known from before by a work done here by Bere, Raul, Claudio Sonia, Alessandro. And there was and then improved a bit by Nico and Raul again. And there was also an approximate theory for this phenomena. This one here. Here, they obtain that the global phase psi obeys this equation. So whenever rho is larger than the mean value of omega, so whenever rho is large enough, this has a fixed point, so the global phase goes to this fixed point and stays there. So that there is no collective activity. The global phase goes to a fixed point and stays there. Then whenever rho decreases and becomes smaller than the mean value of omega, this becomes oscillatory. So then this corresponds to the state of collective firing. And this theory was valid for any distribution of natural frequencies, and also was valid for the case of noise. In the case in which to the dynamics of each unit, you have white noise, independent and correct for each unit. So this was very general, and we thought this is a very general phenomenon. And we were happy with this. But then, recently, Ott and Thompson proposed a method that allows to solve this problem exactly in the infinite size limit and in some cases. The method is, well, it's not so difficult actually. So in the limit of infinitely many units, to describe the system by the probability density of finding a unit with frequency omega at a phase psi. And this probability obeys the continuity equation, which corresponds just to the conservation of the number of oscillators. So this is a very well-known equation. Now, since this is a phase, P has to be 2 pi periodic, and then you can express it.
What is the stat?
This is a complex conjugate. Yeah.
No, R is not.
Yeah. R is the rho times E to the global phase. So this is the global. This is basically center of mass of the system in complex notation.
This is a cosine. This is a cosine.
No, R is rho times E to the E times psi. So this is real. This times the complex conjugate, so this is real. Right.
So to rewrite the sum of all those operators using the order
Yeah.
the complex on the place.
Yeah.
It is exact
It's the same as before, but yeah.
Just a matter of
Yeah, so this equals to rho times the sign of the difference of the global phase with the oscillator. So, okay, you can write the P as a Fourier series, then you can substitute this on the continuity equation, and then you get some equation for the coefficient of Fourier expansion. Now, in principle, this is an infinite hierarchy of coupled equations. The equation for m equal 1 is coupled to m equal 2, and so on. But if these coefficients satisfy this are this form, this is some answer, then you can obtain a closed equation for a well, now here alpha, but it's a, which is this one. This actually defines a manifold, which is so the set of functions which are this form. And this manifold is invariant under the evolution given by the continuity equation. And moreover, they were able to show that this manifold is attractive in the sense that the dynamics of the global parameter, the Noctan dynamics, is given by this one, the one in the reduced manifold. So now we are left with these two equations. We have an equation for each value of omega, since alpha depends on omega. So still this is indeed an interdifferential equation. Again, the star is the complex conjugate. So this is really not so great, but in the case that G is a Lorentzian distribution, then you can do this integral by complex contour integration, and then you can express R as a function of alpha in the pole of G, and then you get a closed equation for by expressing this equation for omega equal to the power of this equation. Then you get a closed equation especially for R. So in this way, you can reduce the system of n coupled equations, this is called infinite coupled equations, to a system of two-dimensional system. So it's going to two ordinary differential equations coupled in this way. And indeed, this method is quite general. You can apply to many different systems, also with external couplings or different forms of the dynamics of the real units. So it's pretty general, but the great thing you can obtain only for the Lorentzian case.
You say that it's very general, but how good is the answer to be?
Yes.
You're using the answers. How good is the answer?
Yes.
Generally, the answer is good, but
this answer is always an invariant manifold. So for any distribution, if you start with a distribution of this form, you stay there. And then for the Lorentzian case, you can show that the dynamics of the global parameter R is given by the dynamics review in this manifold. So in this sense, if you're interested in the global variables, the manifold is good enough. Then this is proof for the Lorentzian case. For the general case, it's not proof, but comparing numerical simulation with this answer, seems that it is also describing the dynamics. Also, this form of the coefficients can interpolate between a state of desynchronization to a state of complete synchronization. So it's pretty general.
So you have in the ansatz
Yeah.
E equal to alpha to the m.
Yeah.
And now you substitute and you
Yeah.
have it to the m. So you had the m before, and now you seem to have root 3 of m.
Yes. Yes.
Why?
Yes. You basically do that each term on alpha,
You can do so.
it's equal. I mean, you do this equation for each term of the summation, and it has to be equal for all of the terms, and it is if alpha satisfies this equation, which is
I alpha is this.
I alpha is yes.
Just to avoid confusion. Alpha
What does that mean? That in the end? So what is that? I mean,
The Fourier summand, Fourier coefficient.
this is a Fourier expansion.
Yeah, this is just a
yeah,
Fourier
so that should be
expansion.
also omega of n or something. Omega is
No, omega is the frequency.
Omega is this is the given frequency.
You do the Fourier expansion only on phi.
on 5.
Yeah.
Exactly. So that's the.
So that's the version omega.
That's the Fourier space of 5.
Yes.
It is.
Yes.
You put as a suffix x because it's discrete.
Yes, because in this periodic. Since it's periodic, it has to be assigned modality.
Okay. And then why is that has to be a power of n?
No, it doesn't have to.
Yeah, but then that's why.
It allows to get a close equation for it. Otherwise, you don't. You get a infinite hierarchy because P1 is coupled to P2 and P3, P3 is coupled to P4, and P5, and you cannot solve it. In this way, you can solve it. And then,
Yeah, that's not a reason to put that. Yeah, they
there's a you can solve it.
What is that? And then yeah.
And then it works. Then you can show that the dynamics is described like
I
this.
understand.
Okay. So with this method, you can solve exactly our problem. You can reduce it to two coupled equations. By doing so, what you see is that actually this regime we were talking about of rectifying is not present. We see here that the synchronous degree decreases before, but here the zeta is always 0 for the infinite size limit, for the exact result, and this is for different system sizes or for large number of units, zeta becomes always 0. And one can actually obtain the full bifurcation diagram of the model by using the previous method, and it's right here. And you see that if you start with the average frequency is smaller than omega, less than 1, this corresponds to excitable system, then you will start in the static regime and you never get into the state of rectifying by increasing the diversity. So we see that in this case, this phenomena we thought to be totally general is not present. And what is this Lorentzian we're talking about? Well, it's this function here. So it's basically a symmetric bell-shaped function, but like a Gaussian or any other. But the thing is that the decay is very slow. It decays as a power law exponential 2, so the tails are very broad, very large. And this means that the variance of this distribution is infinite. Actually, even the first moment is not really well defined. Since the integral that defines the first moment diverges. The first moment is omega 0 because this is symmetric, so as a partial value it does converge, but mathematically, strictly speaking, not even the average is well defined.
Sorry, what happened for negative values of omega?
Yeah, if the omega is smaller than -1, then it rotates on the opposite side. If the omega is smaller than 1, than 0 but greater than -1, nothing really. The stable fixed point is in a different position, but nothing else. So, if omega is -1, the stable fixed point would be either here or here. Here. And if it's smaller than -1, instead of rotating this way, it will rotate the other way. Since we take the average to be near 1, the number of units we rotate in the other side is very small. So yeah, we were very surprised by this result that the phenomenon we find interesting was not present in this case that could be solved the same. So we kind of reevaluate what we knew and see how general this was, to see maybe that in the infinite size limit this was lost, and it was just a finite size effect in simulations or something. So we study different distributions, either uniform, Gaussian, also asymmetrized, exponential, and others. We see that the regime is indeed present. Here, to see what happens in the thermodynamic limit, in the limit of infinitely many units, and to see if then the phenomena is still present, we use this method of Boltzmann and Thomsen. But to apply this for the case of distribution which is not Lorentzian, then you basically have to integrate this equation numerically for different values of omega, and then do this integral numerically. So for distributions, for linear distributions, you can use this, although you don't get really a big reduction, but it allows you to see what happens in the thermodynamic limit of infinitely many oscillators. And we see that also even in this limit, this transition is conserved for the case of uniform, Gaussian, and others. Then we consider a family of Lorentzian-like distributions. These are distributions like the Lorentzian, but in which the decrease is not a power law of exponent 2, but power with an exponent. So exponent, in this case with exponent 4. So it would be like this, but with a 4 here, different organization. And we study the whole family with different values, 3, 4, 5, and whatever. And we see that in other cases, the regime is present. In other cases, but except in the Lorentzian one. This corresponds to the quartic Lorentzian, and we see quite visible even for the Lorentzian, for the purely Lorentzian case, as we saw before in the finite size case, when we have 50 or 200 units, there is indeed still a peak in zeta. So again, in this limit of not so many oscillators, this corrective firing regime is again present. So all this leads us to say that this phenomenon of this diversity-induced transition into a state of corrective firing is indeed generic one, and it's the Lorentzian, the one which is given non-generic results. This is important because since this method by Otto and Thomsen was proposed, it has been used to study different things, such as the effect of delayed interaction, of the effect of bimodality in the distribution of different things, but always taking Lorentzian-like distributions. And here we are seeing that the Lorentzian gives results that are non-generic. So usually when you study one of those systems, you are not so much interested in the particular results of your particular system, but you're trying to get general results. And here we see that the Lorentzian does not give you general results. We also consider a different system of excitable units. We consider a system of Bifurcation oscillators, which are two-dimensional systems which have some limit cycle. We consider a system of analytical units like this, coupled globally, like in this case. And we saw again that for uniform Gaussian or many other distributions, this phenomena was still present, but not for the Lorentzian case. So that's another indication that the Lorentzian is kind of special. Then we tried to go a bit further, and we tried to obtain the bifurcation diagram for the case of arbitrary distribution different from the Lorentzian. And to do so, we did analysis in the spirit of the classical Kuramoto analysis. Here is the dynamics, which can be rewritten in this simpler form. Now B and phi 0 are connected to the global parameters rho and psi. And we focus again on the infinite size limit and in the steady state. The steady state again understood as the one in which the global parameters are constant in time. Then if the global parameters are constant in time, then B and phi 0 are constant in time. And so units with omega smaller than B have a fixed point, so they go to this fixed point right here, whereas units with omega greater than B are oscillatory, and they are rotating with speed, with this speed that depends on the position, the angular position, and then they stationary probability distribution is inversely proportional to their speed, so it's this one here. So taking this together, we have the stationary probability distribution. It exists. So it's this one. And once we know the probability distribution, we can obtain this complex of the parameter. Before we obtained it was defined by summing this factor over all the oscillators. Now it's defined as integrating this factor over the probability distribution. Now the probability distribution depends on those global parameters that are defined here. So this way you have equation for this. These are the parameters. These are complex equations, so corresponds to these two real equations. After some algebra, you can obtain a closed equation for B. This indeed has two solutions, B equal to H plus and B equal to H minus B. And solving it, you would get the stationary value of B. Now, F1 and F minus are defined here, and so depend on the probability distribution, and in particular depend on the variance of this distribution. And by evaluating these functions, we see that for small values of the diversity, there are equally three solutions. One for B equal to H plus and two for B equal to H minus. And increasing the diversity, the solution corresponding to H plus and one of the solution corresponding to H minus, they collide and disappear. So this corresponds to a bifurcation in the system. And interplay corresponds to the bifurcation which leads to the state of collective fighting. In this bifurcation, the stable fixed point disappears, and so it disappears. So by imposing B equal to H plus equal to H minus, this is the condition of the bifurcation, the transition, and then you can show analytically that the transition takes place with phi equal to phi over 2. And then by solving these two equations, B equal to H plus and B equal to H minus, numerically, you can obtain the values of B and the variance at which transition takes place. But that has to be done numerically, since these F1 and F2 are integral functions. But we can also obtain an approximated analytical expression for the critical value of diversity. And to do so, we see that here, this integral only takes values of omega larger than B. So if the distribution G decays fast enough, this integral can be neglected, and then, since you know that in the transition phi is equal to pi over 2, from the first equation you get rho equal to the mean value of omega, and then in the second equation you can expand this as a power series of omega over B. Since omega is always smaller than B, you can do that. And by expanding this, you can do the integration, and to first order you obtain this expression, which is independent of the distribution. If you go to higher orders, then higher order operation do depend on the particular form, but the first order is valid for the distribution. And the distribution which has a defined variance, otherwise this diverges and it doesn't work. And by doing so, you can obtain the bifurcation diagram, this the part corresponding to this transition. And for the Gaussian case, it is something like this. So we see that these lines delimit the region of collective fighting, and for different values of the coupling. So you see that for small values of the diversity, you start in this state of this stationary state, static state, and then by increasing the diversity, you enter the region of collective motion, and then by a further increase, you again lose this state. This is quite different from the Lorentzian case. In the Lorentzian case, this line, which corresponds to the Snake bifurcation, which visualizes this, also starts from 1, but with positive slope, and never enters the region of omega smaller than 1. So in the Lorentzian case, if you start with omega smaller than an average frequency smaller than 1, which corresponds to a excitable system, you never, by increasing the diversity, you never enter the regime of collective fighting. So even though these two phase spaces are topologically equivalent, they are because we can go from this one to this one by continuous transformation. So these two phase spaces are topologically equivalent, but physically they have very different connotations. Since in this case, this regime of this transition to rectifying in this way is present, and no, it is not in this case. So to sum up, the conclusions are that the system of active rotators in the excitable regime show generically diversity-induced transition to a state of collective firing. Then the Lorentzian distribution is the one that displays non-generic behavior. We have also proposed a new analytical method to obtain the connected values of which the transition takes place by frame distribution. And this non-generic behavior of the Lorentzian distribution warrants about the use of some recently proposed methods, the Cotton-Thompson method, to study the generic properties of couple oscillators. And then I give you with some references in case you're interested and to know more details. And that's it.
Thank you very much, please. Are there questions?
Can you go back to this previous one? And here you mean that, so that's a phase diagram.
Yes.
So you consider here sigma as a
Yeah.
parameter and
Yes.
omega as a
Yes.
parameter. Then basically going from the Lorentzian to Gaussian, you are changing the functional form of the probability of the
Yes.
probability distribution of the diversity.
Yes.
Okay. Then the question is, if you could parameterize in a general function that includes both Lorentzian and Gaussian, would you probably now go from one to the other
Continually.
continuously? Exactly. So that they say it's not a Lorentzian, it's not generic.
Yes.
As we call it, but there is a family of functions which
Yes.
has that phenomenon and another one has that.
We have this family of Lorentzian-like distributions, which are like this, but with an n.
Exactly. So
And
we'll be changing.
all of them, but the Lorentzian show this phenomenon. So all of them could be something like this. For large n, it could be something like this. For smaller n, it could be smaller region. And then for the Lorentzian, it really starts vertical and never enters the.
Yeah.
So
Then
the Lorentzian is the first one that doesn't show this phenomenon.
yeah, correct. But then I mean it's probably and then you go. This is because you are using a discrete thing and changing from 2, 1, or you're using it also fraction.
I studied fractions and I was seeing basically the phenomena.
But then probably if Lorentzian is 1, you put 0.8, you get the same thing.
Yes.
For the m equals
Yes.
1 is the threshold from super to super.
It seems so. Yes.
So it's not that Lorentzian generically like that, it's just it's a threshold.
Yes.
Could you repeat this? So it was, what is the threshold? Is
The Lorentzian.
no, I mean, but it's the decay exponent. What is
Yes.
exponent 2 is what is the threshold? So
Yes.
smaller than 2
It
is.
seems so, yes. But the Lorentzian is very important because thanks to this method, you can solve many different systems of couple oscillators. Exactly. You can reduce them to a small number of couple ordinary differential equations. What we see here is that in this case at least, the Lorentzian in particular is not generic. So that's why this is important, because people is using the Lorentzian to study different things. We say,
You will say it's not that it's not generic, it's that it happens to be a family of function that shows that behavior instead of the other.
yeah, but
No, it's not a family of functions. It's the Lorentzian that shows that behavior.
but there are
No,
more.
you put
There are
them
more
less than 1, you go
Because
to
the Lorentzian with exponent
That's
1.5, again you don't. I mean, if it takes
well, if you put a Lorentzian with a exponent 1.5, you cannot normalize it.
No, 1.5 you can
And you cannot define the value mean value.
later for the range.
That's the point. I mean, if you have a distribution that has the Lorentzian has only a mean value well defined, if you use the principal value for a data. If you have a function that has a mean value which is not required that, I mean that is well defined by itself, then
But the point, so both the Lorentzian and the Gaussian are Fourier transforms of Lebesgue stable distributions. You can make change continuously by putting a Lebesgue stable, and the Fourier transform are this family. And then the transition is when the Lebesgue exponent is 2.
It's usually, but people never uses a Lorentzian exponent 1.7.
It's fine, they say that it's not the generic problem of the world.
Well, when people study Levy flights and all that, they do that.
Okay, but if you consider a system of rotators,
Well, it's just a question of
as
size.
a probability distribution, you will in principle
You can do it.
you use Gaussians or Lorentzian because of this method, and we say, okay, Lorentzian gives different results than the more usual distributions.
No, we do have a conjecture, which is that the distribution will have a well-defined second moment. Will show rotation. And those who do not have second moment, otherwise,
In fact, our
No. A cubic Lorentzian has infinite variance and yes, so
cubic Lorentzian won't be.
cubic Lorentzian.
We don't need second moment. We need first moment without principal moment.
Yeah, it seems so.
That's it.
So
Yeah, but I think this is the important question. When you say generic,
Generic means
I mean, for instance, probably many people would say that a generic probability distribution is a power law. So, I mean, there are more power laws in nature than Gaussians or Lorentzians.
truncated power law. Truncated power law. There are many.
truncated powers, there are many. You see that
So what happens with power?
If you have any distribution that
Let
is
him answer. I'm asking. This is an example.
for a power law with the K exponent greater than 2, we see the phenomenon. If it is smaller than 2, we don't.
But then it
And
goes
if
in
it
the
is,
direction of
if it
control
is, if it is smaller than 2, but it's truncated, we see the phenomenon again.
any
We check that.
distribution that is truncated, and there is no distribution in the physical universe that is not truncated. Any distribution that is truncated, we see that.
And anyway, generic means that the infinitesimal deviation from that change abruptly the phenomenon. That's not the case here. So that's not generic in that sense. But that may be just
Lorentzian, if you try to change the exponent,
you still get it. Then it's generic.
In this case, in this graph here, so what is happening is that the sneak line, instead of just going up, it first goes back and then it goes up.
yes, it does
Having that the whole thing, I mean, if it
No.
still looks like a cat, and
apparently, yes. Apparently, then there are different things
Then the
here,
thing is the
but
same.
we were more interested only in this sneak line because it's the one which gives the.
yeah, well, but it's just valid for small values of delta. Delta.
Yeah, the target will kind of point over there at the head of all these things.
Yeah, it seems. Yeah, it's.
So there is a cat.
I mean, it change the position, but
It seems that there is also this element is off. And
sorry, that's not the
it seems that the free space is the same. But
It's a type of-
Este lo sabe usar, ya. Hasta que vuelva a ser así, eso sabe no sobre.
Yeah, if you go into the one before last, this figure. I'm curious because here, I mean, in the case in which you have the phenomenon, I mean, you have this elbow.
yeah.
So it seems that the dependence on K and coupling is very mild. On the other hand, you were saying that, I mean, for instance, this modified Lorentzian, I mean, the elbow would be much to the right. I mean, do you have any qualitative theory of which are the factors that influence the elbow? So the leftmost omega, I mean, the turning point, whether it's more to the right or if there's a maximum value.
Yeah, we haven't really.
What does it depend?
We haven't really studied that in detail, but it seems that for large values of K, this is bigger, the regime of qualitative filing. And for very small values of K, this is somehow gets smaller and it's a bit different. But yeah, it depends. Also depends on the random distribution. For distribution with the K is faster, it's larger. For distribution with the K is slower, it's smaller. But we haven't really studied much detail.
You studied the active rotators,
Yes.
and you have found this effect. Is there anything that depends on the shape of the distribution for looking when you see that the normal rotators?
For the normal rotators, if the distribution is symmetric and unimodal, the results are relatively the same. That's why people is using any distribution basically, because in the original case it doesn't matter, so for other cases they also using any distribution which is symmetric and unimodal. If it is not unimodal, then there are different. Transition can be subcritical and can be different things, but if it is symmetric and unimodal, as usually they are, then the phenomena are the same.
Any other? That's not the case. Let's